All right. So let's actually look at what you need to. All right. So you can see here on this page that I put the third lab up, and you can go ahead and download that. I've already downloaded it. So once you downloaded it, open it and place it in a location on your hard drive. I'm going to put it on CSA and unzip it into there. So now I've got week 3 right there. And go ahead and open up week 3, the lab. All right, and we'll go over the general idea here. Well, actually, before we do that, let's also, inside of week 3, this week I did something different. I actually saved a starting point MXD, so you don't have to add the data. So if you double click on that, a map document will open that has the data already loaded into it for the lab. Excuse me. Okay. I'm going to close up this window. Yours may look slightly different. Okay. All right. So, for those of you who don't know, you probably all know that that's Europe. So this is the data that we're going to utilize. We've got a source, a destination. So we're going to be doing cost, distance, and least cost path modeling. And then we've got 2 data sets that I actually got these from the internet. An elevation data set for, it's actually a worldwide elevation data set, and a land cover data set. The land cover data set had all sorts of different land cover values, but I simplified it down to 3 different values. The values in this data set are 0 for water, 1 means open areas, and 2 means forest. 0, 1, and 2, forested cover. And these are just worldwide data sets that downloaded from the internet. So we're going to use them in our scenario. Okay, so basically, our scenario is that we're going to design a path to travel between 2 points in Europe. Okay, and we want our model to allow the user to specify the costs for travel, and so they'll become parameters. And we've reviewed that a few times, but I'll make sure that you know that when we start building the model, how to do that again. Okay, so we've got water, we've got open areas and forests, and we're going to provide some method for converting the cost that they associate with those into a cost surface. We have to include a few other things in our cost surface. One will be the slope. Okay, the slope data set has to be. Oh, I have that on here. Sorry, it's warm in here, especially when you're up an extra foot. Just kidding. I don't know. Hot air is supposed to rise, right? Okay, so in addition, they're going to be able to provide a cost associated with traveling over various slopes. So the higher the slope is, the higher the cost. And they should be able to add that cost in. And then lastly, we want to create a transition cost when you have to change between traveling over the water and traveling on land. Okay. So the idea there is that if you were traveling over land, you would have to be using a different mode of travel. So you might have to, acquire boats or vice versa if you're traveling from a boat to land. So there's a cost associated with that activity. Okay. All right, you're going to use the provided data, and you're going to make a toolbox, and then you're going to answer this one question here. You're going to experiment with several different values until you find one that chooses a mostly overland route between the 2 points that I have here. The red one is Copenhagen, and the yellow one is Venice. Okay, and a mostly overland route means that it travels, through here, rather than traveling around like this. Okay. It's impossible to get a purely overland route between these two places. If you zoom in, Copenhagen is actually on an island, so you can't get purely overland route, but you can get close. Okay. All right. So how are we going to solve this problem? Well, first off, before we even start building our model, something that I wanted to convey is that oftentimes when we go to create a model, if there are pieces of our model that are going to run and be exactly the same every time, in other words, if there's something that's going to occur in our model that's always going to be the same thing, and isn't dependent on any user inputs, we should often try to do those things beforehand. That way, they don't have to run every time our model is created. And so, let's think for a second about what those are. Okay, and since we haven't done this before, I'll go ahead and mention the first one that comes to my mind. So we have an elevation data set in our in the given data here. Okay, elevation is one of the data sets. However, our costs are going to be determined by slope, right? And so if we included, an elevation data set in the model and converted that to slope, every time our entire model ran, that process would have to run. And that's not necessary, because having slope, converting from elevation to slope is a single process that doesn't require any inputs that we're concerned about. And so it'd be best to go ahead and create that data set beforehand, so that we don't have to create it in our model, and every time we press the run button on our model, it doesn't have to redo that. It's always helpful whenever you go to create a model to say, okay, this model assumes these steps have already been taken, so that you don't have to redo those steps and add to the processing time. It's particularly helpful like when you share your models. People might say, oh, that model takes forever to run. Well, if you try to weed out the steps to help the model run faster, that's a better way to approach it. So let's go ahead and calculate slope for this data set. I'm going to go ahead and turn the land cover data set off. You see, that's the data set that we're talking about here. And we could calculate slope in the Spatial Analyst terrain tool, or surface. Calculate slope for elevation. Just going to drag the elevation data set in there. And then I'm going to specify where I'm going to save it. And I want to save it in the same location that I'm working in. CSA files might be different on your machine. Oh, that's actually from last week. So let's change it to CSA Lab 3 data. Okay, so now I've got elevation and I've got slope. I'm going to save it in there. We're going to leave slope as degrees, and then we should be good here to just hit OK. Notice that the values here have already been adjusted. I mean, for Europe, I don't know exactly how tall the Matterhorn and that rest of the Alps are, but they're much higher than 4,536 feet. So we can assume that the data is already in meters here. So if I hit OK, it will run through and create a slope grid. And so that's our slope grid. You notice that there's some pretty serious slopes here between Copenhagen and Venice. One of the reasons why I chose those two areas. Okay, what other things can we do beforehand? Well, one thing is that if we include it, what are the values of the raster in these white areas right here? What's the value of the raster right here? You can go ahead and hit identify if you want. What did you say on the coast? Yes, no data. So if we add this slope grid to a different grid, what are the values going to be there? There's still going to be no data. Okay, no data plus anything from an earlier lecture. No data plus any other value is no data. And so if we want to include this in our data, we need to change those values there to a different value. So let's think about that. How do we do that? We can do that in map algebra. We've done it before, but this will be a good review. Okay. We can use a conditional operator, and we could say if the slope, and we could use this operator right here, is null. If is null has to be capitalized. Slope. This is the first value is going to be if it is null, if that's true. Okay, we're going to assign it a value of 1. If it's not null, we're going to assign it the value of slope. In other words, the slope out in the oceans will be 1, a very low slope. We could make it something even smaller. It doesn't really matter. It does help if you don't make it 0. I guess yeah. It'd be fine if it was 0. In fact, that might make more sense, right? Because it's totally flat. Okay, although we got waves and whatnot, but it's totally flat. We can let the user compensate for the costs to travel over the ocean when they enter that value. Okay. So slopes aren't really a factor over the ocean. So if we make this 0, it'll make it so that there's no slope over the ocean, therefore no slope cost associated with traveling over the ocean. Okay, let's save this as a slope. I'll call it slope. I don't know what. Slope no null or something. Got no null values or no data. No data value sounds too. All right. So okay, I'm saving it into the same location. It's saving into that folder. And so now what I get, it looks different because it colored it different. By default, when you do slope, it assigns this code to it, these codes to it. We could, if we wanted to, go into the slope no null data set, double click on it, go under symbology, and say, I want to steal the symbology from a different layer. It's this button right here under symbology. This little folder, you say import, and you choose a different data set. So we could choose regular old slope. Okay, so you got to go hit classified first and then do it. It's telling us we can't steal it unless it's the same classification scheme. And then you hit OK. So now I can just get rid of slope. I can right click on slope. I don't need to see it anymore. So I've got my slope no nulls value here already processed. So that's one of my inputs. All right. Let's think about what our inputs are going to be. We're going to have one input for land cover, one input for slope, and then finally we're going to have this transition cost. We're going to have transition costs associated with it. So we need to find all the boundaries between water and land. So we've got this data set. I'll go ahead and turn that data set back on. So let's zoom in here. Okay. So we need to find all these boundaries between water and land. Okay. And there are a few ways to do this, but I said in the lab, the way that I suggested and the way that we're going to demonstrate here is to use the majority operator. Okay, so you can do that using the focal statistics. You can choose. Did I say? Yeah. I meant to say variety. Could you change the lab? Yeah, majority won't work. I meant to say variety there. I know I said majority. I'll change that lab. And this is being recorded, so at least it'll be in the video. I'll change the lab so that it says variety. Okay. Why variety instead of majority? Well, variety will tell you how many different values you get in a moving window. So if you get more than one value in a moving window, then you can assign a higher cost to that area. That's a transition. Okay, if you get the same value everywhere in the moving window, there's no transition associated with traveling across that cell because everything in that 3x3 window is the same. And the reason why we're going to choose a 3x3 window is so that can be as small as possible. You're only going to get a transition cost associated with traveling through that cell if it's a boundary cell, okay? Because we're only looking at the cells to the right and the left and up and down. Okay, now let's think about this though. If we do a variety, and let me look at the help here, or show you the help. If you look at the variety, it's going to count the number of different values that it gets in its window. So let's think, how many different values do we have in this land cover data set? How many different types of values? 3, exactly. We can get zeros, we can get ones, or we can get twos. And what we want to do is make it so that anytime that we have both a 0 and a different value, we get a variety that's different than if we get either all zeros or all different values. So we're going to have to do a little pre-processing here before we run the variety, because we don't really care about the difference between going. There's not as much cost. We're not going to model the cost associated with traveling between an open area and a forested area. Although there might still be a travel cost associated with that, we're not concerned about modeling that because it's not as significant as the cost between a water mode of transportation and a land mode of transportation. So we're mainly looking for the land-water interface. Okay. All right. So what can we do to change this data set? We could do a reclassify. I'm going to do a another conditional operator. I'm going to take the land cover data set, land cover, and then I'm going to say if the land cover equals 0, then the value is going to be, I guess we can just leave it 0. If not, it's going to be 1. So we're going to make either zeros or ones depending on whether it's land or water. And I'm going to save this and just call it land water save. So I've got the conditional operator. It's going to take the land cover. If it equals 0, it's going to be 0. If not, it's going to be 1. So we're only going to get zeros and ones in this data set. It's going to be a land water mask. Now I hit OK. That'll run through, create a new data set where I've got land and water. It's not symbolized as nice, but it's still symbolized. Okay, and this you'll be able to see that this will prevent, like, if I was going to travel across this landscape, and let's say it was a lower value to travel across water, I'm not going to get it's not going to favor this area because it's going to be transition costs associated with going through this area and saying, okay, well, I'm going to go in the water for a little while and then I'm going to get out of the water. That wouldn't really happen in real life. So these inland water bodies won't be favored. Okay, so now we can do our focal statistics. Focal statistics, we're going to choose the land water mask. And we're going to save this as boundary. I'm just going to call it boundary areas. And then I'm going to leave it 3 by 3, but I'm going to choose variety. Like I said, variety is not the only one that will work, but majority definitely wouldn't work because all it would do was change where the exact boundary was. Majority will choose it will choose as the output value the value that is most often seen in the window. For example, I've said there's other ways to do this. We could do this by, let's say we had values of 1 and 2 instead of 0 and 1. Let's say we had values of 1 and 2. Then we could do the sum. And anywhere where the value was 3, we would know that that was the window. So I'm going to do variety here. Say OK. And this is going to run through, and it's going to create a boundary. See that? Boundaries that it's created. So all those areas right there, we can assign a different cost associated with each of those. All right. So at this point, we could start building our model. Okay. Another thing that we could do is to process it a little bit further. We could come up with a layer that represented each of the land covers and was just a binary, 0 or 1, meaning it was. So if we have one data set called water, with 0 meaning not water, 1 meaning water. Then we could do another data set that had open areas, meaning 1 was an open area, 0 was not an open area. And then land cover, we could have another one that was 1 meaning forest, 0 meaning not forest. And the reason that we might want to do that is that it would be easy to do a multiplication problem that looked like this. Let's look at this. I'm just going to open up a new Microsoft Word here. So let's say we have our water, which is our binary water times the cost plus the binary forest plus the cost. I mean times the cost plus the binary open times the cost plus the binary boundary plus the times the cost plus the slope cost. And then I would, put all these in parentheses. So this is kind of our pseudocode. This is what we need to do. So part of our model could be, breaking apart those data sets to make that. But it's probably easier to think about in our minds and a little less processing if we come up with each of these binary masks: the water binary mass cost, the forest binary mass cost. The water binary cost, the forest binary cost, the open binary, the boundary binary, and the slope data set that we're going to multiply times cost. It's not going to be binary. Slope's the only one in here that's not binary. All the rest of them are either going to be ones or zeros. We're either going to have that cost or we're not going to have the cost. So we could come up with these binary layers: water, forest, open, boundary, before we even put them in our model. Is another thing that we could do beforehand to make our model work better or more efficiently. So let's go ahead and start with boundary areas. The boundary areas is already close to what we want. We're just going to run a few more conditional operators. I'm going to take my boundary areas and say it looks like it's the 2 that's going to be the cost associated. So if boundary area equals 2, assign it a 1, else assign it a 0. Boundary area equals 2, make it a 1. If not, make it a 0. That's going to make it binary. I'm going to save this in the same area. I'm going to call this boundary areas binary. I've made my binary boundary areas. In fact, I'm going to call, instead of calling it boundary areas, we'll call it transition. Transition binary, because that's what I called it in the lab. It'll be the transition binary. I'm going to hit OK, and it's going to make 1s everywhere that there's a transition between water and land. So these are all my water-land transitions. Now I'm just going to repeat this process with land cover. I'm going to say con land cover equals 1, and say it's going to be 1 if it's water, 0 if not water, and then just call this water binary. So now I'm going to get 1s where it's water, 0 where it's not water. I'm going to copy this. Run that through. So that's my water binary mask. Run the raster calculator again. And I'm going to get land cover equals, oh, I messed up, didn't I? Because water was 0. Okay. I'll just go like this. If you don't, under geoprocessing, if you go to geoprocessing options, if you have overwrites checked, go back and check overwrite. Then what you can do is under results, you can run, if you open this up, you can run the last thing that was ran, and you can just change this to 0 and run it again. You change the equals to 0, and it'll now be a 1 in the area that was water. Okay. You have a question? No? Okay. Double click that guy again. And now you can just change this to 1 and call this open binary or open areas. And you can do it one more time and make it 2 and call it forest binary. Okay. Forest binary, hit OK, and run through it. And at this point, you'll have data sets that represent each of these land cover types. So here's my forested areas. See the forested binary? So those are all the forested areas in Europe. Okay. This layer represents all the open areas in Europe. Okay. Basically meaning like agriculture. And we've got North Africa here. Most of this means desert. Non-forested areas is what that basically means. And then this one is the water binary. Okay, so all the ones, all the green is open area. I mean, it's already water in that one. And then the transition costs. So those are all the transition costs, or the transitional binaries. And then these are other data sets that we created kind of in between. So this data set, forest, open binary, water binary, transition binary, and slope no null, those are going to be the inputs of our model. So we've done a lot of the processing that would have to be done over and over again in a model. And we're going to have the model just ask for the multiplicative factors for each of these. So the model will provide a multiplicative factor for forest, a multiplicative factor for open, water, transition, and slope, and then run through and do its thing.
Can you show the forest binary definition?
Sure. It's the last one I did, so it's right there. So this is saying if the land cover equals, which means if the land cover is equal to 2, for every cell, if it's 2, assign it a value of 1. If it was a value of anything else, assign it a value of 0. All right. So if we just added these all up right now, we'd get a lot of 1s in our data set, but that would be like saying the cost was, that'd be like saying we're not weighting each of these. So we're going to assign weights to each of these that represent the cost for each of those areas. So now at this point, we can start making our model. So if we go into Arc Toolbox, hit Add Toolbox, and then create a new toolbox in this directory, which is going to be C, I put it in SA, Lab 3. I'm just going to put it right here and create it and call it Lab 3, the Lab 3 toolbox. I'm going to open it. So now I have it there, and I'm going to create a new model inside of it. Okay. You can change the name of the model later. But we've got our model there, and the first thing that we need to do is the first part of our model is going to be creating our cost surface. And our cost surface is always going to be the combination of those layers in here. It's going to be the combination of water, forest, open, boundary, and slope. Okay. It's always going to be the addition of those factors after they've been multiplied by their respective costs. So that seems like a great candidate for the for map algebra. Okay. All right. Now, what I would like to do first is we've shown with other tools how you can make them parameters, but I want to show you that you can create variables at any time. So I'm going to create the variables that will represent the costs. So if I right click here and say create variable, I can create a new variable that can be of any data type. Okay? Well, there's lots of different data types that I can use. I want to create a data type that is a number. Now, in the GIS world, this is kind of like in ArcGIS's world. These variables are kind of like programming variables, and I know that not everybody here has been in a programming class, but it actually has a few different types of numerical values, and we want to be able to specify a number, and there's integers. You can specify an integer that's called a long integer, or you can specify a they call it a double for a floating point value, one with a decimal place. Okay. You can specify either of those as possible numeric values. Let's think for a little while. We want to express cost. I don't know that we need to express cost as a floating point number if our costs are going to be high. So we might be able to think about our costs as dollars. I know that they don't use dollars in Europe, so maybe that's bad. Or we could just specify it as time, and time might be easier to conceptualize in this case. Let's look here. I'm going to cancel out of this. Go back. You don't have to cancel out of that because we'll be right back. Just going to minimize this. Forgot the cell size, so I'm just going to check on that real quick. I think it's pretty large, though. It's either 90 or, okay. It's 1,000 by 1,000 meters, so it's a big cells. So maybe we'll think about our costs in terms of time, and we'll think, you know, you're traveling 1 kilometer in this type of environment. How long is it going to take? How long is it going to? How much additional time is this factor going to add to your overall time? Okay. All right. So if we think about how long it takes to travel a kilometer just walking on an open road, how much time do you think that would take? Somebody come up with a guess. Walk what is that, a half a mile or a little less than a half a mile or a little more than a half a mile? 5 minutes. What's that? 5 minutes? All right. So we can express our values as numbers. I'm going to go ahead and use the floating point number, the double, because that way they can express a number as something 0.5. So if I add a number on here, okay, and make this a parameter, then when somebody goes to run this model, I probably have to save it. When somebody goes to run this model, they will have that option, okay. And I can call this something else. Like I can call this I can rename it and call it water cost. Now I have that value, water cost. If I save it and somebody clicks on the model, they'll see that that's the water cost associated with it. And they'll be able to enter a number that's, you know, with a decimal place if they wanted to, 33.5 or whatever. Okay. All right. So I've got water cost. I've made it a parameter, and now let me go ahead and show you. If I drag on my spatial analyst tool, drag on map algebra, oops, raster calculator, because I'm going to combine all these costs if I double click on this, that parameter shows up. And I can do something like say, okay, the water binary times the water cost is what's going to be the output. We're going to go change this in a second, but I'm showing you now that it will do that for us. It'll make that connection, and that's a valid connection. We don't need to let the user choose the water binary data set. That's part of the model. So that's data that's part of the model. We're allowing them to choose is the water cost. Okay. For now, I'm going to delete the water binary, and we'll put all those in at the same time. So let's make additional variables. Create variable, double. We're going to make an additional data set for each, an additional variable for each one. It's going to be a double. We got to make it right click, make it a parameter, and we're going to call that parameter something different. Let's call it instead of water cost, we're going to call this one open cost, traveling through open areas. And we'll do that again. Create variable, double. Make this a model parameter. And make its cost be associated with forest cost. We've got two more to make. So I'll create another variable. It's going to be double. Make it a parameter and rename it to transition cost. Create another variable, double. And this one's going to be a model parameter, and it's going to be called slope cost. Right. We got all our data sets there. Water cost, open cost, forest cost, transition costs, and slope costs. Okay. Now we can revisit the raster calculator that we just made and come up with the function. And the function is going to look just like this function that I wrote here, but it's going to use the actual values in our data set. So water cost times the water cost times the water binary plus the forest cost plus the forest binary, and so on. Okay. So if we go into the raster calculator, we can create our big expression. So far, I'm just going to delete this because we'll just do it all from the beginning. So we say water cost times the water data set. And I'm going to put them in parentheses. I know multiplication, that should already work, but I'm not trusting. Open cost, put these in parentheses again. Open cost times the open binary data set plus the forest cost. I didn't do forest yet. Forest cost times the forest data set plus transition costs times the transition data set plus the slope cost times the slope data set. Slope no null is what we ended up calling it. We don't want the null values, otherwise it won't produce a cost. All right. Now here, let's go ahead and save this so that each time through, if we have override outputs on, this shouldn't be a problem. If we have the ability to override outputs, it shouldn't be a problem. Let's go ahead and save this so that we can inspect it each time. This one will be called the cost surface. Save it in that location there. And I'm going to say OK at this point. I'm going to hit the little align button and zoom to the, I know this is pretty small. Zoom out a little bit more. OK. Now you notice that it doesn't say it's ready to run. So let's come up with some values that we think would be valid for each cost. Okay. So traveling a kilometer over open areas, we said will take about, what, 5 minutes, did you say? Okay, so we can give it as a 5. Let's use minutes. Okay. Traveling in forested areas, you know, we might be hopping over logs, traipsing through little wetlands or whatnot. It's going to take a little bit longer. So I'm just going to put 10. Come up with different values later. Play around. Water costs. Traveling a kilometer over water, I don't know how long that would take. It probably depends on whether we got a speedboat or what kind of boat we have. Let's say we're just talking like the old days, and this is a sailboat. So it's going to be even a little bit longer. It's going to be 15 minutes to travel over water for a kilometer. Transition costs are going to be the cost to travel between water and land. That might take like up to a day to prepare. So we could put something like 3,600 for a transition cost. Really penalize that. Okay. And then slope cost. This is a little bit more tricky because it's a kind of an additive factor. If it's more sloped, it's going to take us more and more time to go up there. So if we took slope and multiplied it by, I don't know, maybe 2, the highest value we'd get is, because the highest value we have is like 40 for slope. If we multiplied it by 2, we'd get 80. That seems a little bit harsh. Maybe we just leave slope right now to be multiplied by 1, or maybe even later we take it down a bit below 1, because we can multiply things by other numbers. All right. So we've got our slopes. I mean our costs there, and now everything turns valid. And those are really default values. If I save this and minimize it and try to open my model, I have those values in there as defaults, but I can modify those. So I'm going to go ahead and run this right now. Okay, it's gonna create a data set. This might take a few minutes because it's nope, not too many. Okay, didn't add it to the display. Let's make it do that by default. Add to display. So I'm gonna go ahead and run it one more time. By the way, I'm going to save this Lab 3 document just so that I have the document saved as soon as this executes. Huh. Still didn't save it. I'll just go ahead and add it. I did put it in there. Cost surface. I'm going to say yes. All right, here's my cost surface that was just created. And you'll notice that the most costs associated with these transitions. It's really going to steer clear of the transitions. But if I select inside of here, you'll see that I do have different costs associated with traveling over different areas. See that? So the different costs associated out in the ocean. I have pretty much constant cost because the only cost is traveling over open ocean areas. Okay. All right. So If I open up my model again and change one of these values, like let's say I change the water cost to 10, and I run it again, the reason I'm changing that is because it's easy to see the difference that it created. So now if I run this model one more time, you'll be able to see that in the open ocean areas, I don't know why it took that layer off, but I can add it back in, and I can select the values out here. Now they're 10. Okay. All right. I'm going to close this right now. Say yes. I'm going to save it, and I'm going to call this, least cost path. Now I'm going to open it again, edit it. So really the last thing that you need to be able, I have it minimized. Whoa, that's crazy. The last thing that we need to do to finish up this model, I'll let you do that from this point, is to drag on. I don't know why it doesn't. I want to do like a partially open. There we go. There we go. Is to drag on the tools that we need for our model to make this a least cost path model, and run that. So we've got two things to do here. Anybody remember what those were? We got two more tools that we need to utilize from this data from this tool set. What are the two other tools that we need to get this to work? From the demonstration from the lecture on Tuesday, we need cost distance on here. We need one more to get the least cost path. The cost path. Okay, those are the two tools that we need to finish those off. So if you hook those up and you run your model, you'll be able to see the least cost path modeling in action, and you'll be able to answer the question, send your toolbox in. You should be all set at that point. Anybody have any questions on what you have to do? I tried to teach some of the concepts that we learned here today. We're creating variables independent before we dragged operations on. Another one of the concepts that we learned in Model Builder today was that sometimes it's helpful to execute portions of your model that will have to run every time beforehand, so that they don't have to be included in the model itself. All right. Remember this output backlink is in the lecture we called it the cost direction, and it is necessary. It's one of the inputs to the cost path. Okay. Also, I said in the lab that part of your model should be outputting a vector line that represents the least cost path, and so you have one more data set to put in here, or one more operation to put in here, and you can find that one. This always tricks me. Conversion used to be under data management, but since 10 it's not. You can say from raster to polyline is probably the best one that I would choose. You can choose different ones, but that's the one I would choose. It creates a line along the least cost path. Okay. All right. So once you get this running, it takes a few minutes to run the actual least cost path model. Once you get you running, experiment a little bit with the values. You can even experiment with moving the source and the destination around. And yeah, actually, under your source and destination are going to be inputs into these, right? So you're going to have source being input right here, and destination is going to be an input right there, just to get you. So those are going to be inputs. You could even have those be input parameters. You could have the user be able to select whatever source and input that they wanted to select. All right. I'll go ahead and stop the video, the Hangout video there. If anybody has any questions, I'll be here. And